This is my Lab 1 constant velocity video presentation. Lab 1 focuses on analyzing the motion of an object moving at constant speed with no change in direction. This can be done by taking a video of an object moving at a seemingly constant speed and using Tracker to document the object's position versus time in order to extract observed data. Afterwards, GlowScript can be used to create a computational model that reflects the predicted data. We are interested in studying this because it uses Newton's second law to reveal information about how objects move in the real world. This has important applications to fields involving kinematics. The main focus of this lab is on Newton's second law, which states that the rate of change of momentum is directly proportional to the resultant force applied, as well as in the same direction as that resultant force. If there is no change in net force, then the velocity remains constant. Now let's take a look at some equations. One form of Newton's second law as an equation is change in momentum equals net force times change in time. We can get the formulas for final velocity and final position, which allow us to update each value. This model was chosen to examine the system because the iterative qualities of Newton's second law allow us to use the initial conditions of a mass system to look a short time into the future and predict the new velocity and new position. The diagrams below show another representation of Newton's second law and represent how force affects acceleration and disrupts constant velocity. This is a video of a ball rolling at seemingly constant velocity in Tracker. And these are the experimental data graphs plotted in Tracker that reflect position and velocity. The lines of best fit are in pink. In GlowScript, I entered the initial position and velocity vectors from the initial values found in Tracker. I updated the velocity using the formulas based on Newton's second law. Position was also updated using a formula that comes from the fact that velocity equals change in position divided by change in time. Net force is set to 0, and the time for the while loop is set to the maximum time frame in Tracker. These are the predicted data graphs from GlowScript. The results from GlowScript and Tracker were combined to show this graph. The graph shows the experimental position versus the model position. From this graph, you can see that the model position is increasing at a faster rate than the experimental position. This is because the model was coded with a greater velocity than the actual velocity of the ball. The two graphs are similar in that they both reflect a direct linear relationship. This graph shows the experimental velocity versus the model velocity. The graphs are similar in that they both reflect the change in position over change in time. However, the experimental velocity varies quite a bit and decreases overall as time passes. The model velocity remains constant. The fluctuations of the experimental velocity may be due to a variety of factors, such as friction or air resistance, which act in the opposite direction of the motion of the ball and decrease velocity. Another factor could be incorrect experimental position values due to inaccurately clicking on the ball's point mass in Tracker. To improve prediction or data agreement in the future, we can look at a shorter time frame in Tracker to avoid the effects of friction taking place. Additionally, we can make sure that we document accurate and precise point masses in Tracker so the data will accurately reflect the observed motion. How would the results change and remain the same if the axes were flipped? One way the results would remain the same is that the position versus time graph would retain its overall shape, which reflects a linear relationship. The results would also be different because the position graph would show the increase in time for equal increments in position, while the velocity graph would show the time for equal increments in velocity. Is it possible to say how many pushes and pulls are added together to give zero net force in the case that you observed? It is not possible because net force acting on a system is the vector sum of all of the forces exerted on the system by all the objects in the surroundings. Since we do not know information about the surroundings, we only know about the system, and therefore we would need more information. In conclusion, the results of the observed and predicted models varied quite a bit due to possible factors such as friction, air resistance, and human error. Overall, this lab covers important concepts regarding Newton's second law, as well as the relationship between position, velocity, and acceleration. Thank you for watching.